Welcome back. In this video, you'll learn how to find the area under parametric curves. Let's get to it. All right, so earlier in calculus, you learned that the area under a curve can be calculated by integrating the function that represents that curve over the values of x that the area lies between. And up until this point, those curves have always been represented with rectangular equations, or functions only in terms of x and y. But what if our curve is instead represented with parametric equations? Right? For example, take a look at this curve right here. This curve is a plane curve, or parametric curve, that is represented by these two parametric equations, x equals f of t and y equals g of t. Both x and y are defined in terms of a parameter, t. And so if we wanted to calculate the area beneath this curve, how would we go about calculating that area? Well, let's imagine for a second that we don't know the parametric equations that represent this curve, but instead we know how to represent this curve with a rectangular equation in terms of x and y. Right, let's say that this curve is represented by some rectangular equation y equals capital F of x, some function in terms of x that represents y. And we want to calculate the area beneath that function or beneath that curve between two values of x, a and b. We can calculate that area using a definite integral, right? The area is equal to the integral from a to b of that function capital F of x times dx. And so this is nothing new. We know how to calculate the area beneath a function between two values of x, but how could we do this parametrically? How could we calculate the area beneath this curve using our parametric equations instead? Well, since these parametric equations represent this curve, and we're also saying that y equals capital F of x also would represent this curve, what we can do is make some substitutions in this integral. But before we do that, what I first want to do is rewrite capital F of x with y, right? Y is equal to capital F of x, so we can replace that with y, and it would be the same thing. So we'll have that the area is equal to the integral from a to b of y times dx. All right, and now that we have it in this form, we can begin to see how we can rewrite this integral in terms of t rather than in terms of x, right? Because y is defined with a function in terms of x. So this integral is an integral where we're integrating between two values of x for a function defined with x with respect to x, right? That's what dx tells us, that we're integrating with respect to x. We want to rewrite this integral in terms of our parameter t. And so what we can do is begin to use our parametric equations to make some substitutions in this integral, right? We know that y is equal to some function g of t. And so we could replace y in this integral with what y is equal to in terms of t, right? We could rewrite this integral to be the integral from a to b of g of t times dx. All right, now of course we don't want to leave it in this form because you can't integrate this function defined with t with respect to x. And so what we want to do next is change dx to be dt. We want to integrate with respect to t, right? And so how can we rewrite dx to be dt? Well, what we can do is take the derivative of our equation for x from our set of parametric equations, right? If we take the derivative of x with respect to t, that will be dx dt, and that would be equal to small f prime of t, right? The derivative of x with respect to t is dx dt, and the derivative of small f of t is small f prime of t. And now what we can do is solve for dx by multiplying both sides by dt, and that will give us that dx is equal to small f prime of t times dt. And so now we can see that dx, this dx right here, can be replaced with small f prime of t times dt, which will help us get this integral in terms of t, our parameter, right? So we can remove this dx and have f prime of t times dt. And so now our integral is almost entirely in terms of t. We have that the area is equal to the integral from x equals a to x equals b, right? These bounds of integration are still in terms of x, but then we're integrating g of t, a function defined with t, times f prime of t, another function defined with t, dt. We're integrating with respect to t. So we're almost there. The only other thing that we need to change are these bounds of integration. And that's going to be pretty simple. All we have to do is find the values of t that would correspond to each of these values of x that make up the bounds of integration. And so what I'm going to do is just rewrite those to be two values of t, t sub 1 and t sub 2. T sub 1 is the t value that corresponds to this value of x, and t sub 2 is the t value that corresponds to this value of x. All right, so t sub 1 corresponds to a, and t sub 2 corresponds to b. And then the rest of our integral will remain the same. We'll have g of t and then small f prime of t times dt. All right, and what we have right here is an integral that we can use to calculate the area beneath the curve represented with parametric equations. We can find the area under parametric curves using this integral. All right, and so to summarize, to find the area under parametric curves, we can use the following integrals. The area is equal to this integral in terms of x. We have the integral from x equals a to x equals b of y times dx, and that can be rewritten to be an integral in terms of t, which will be the integral from t sub 1 to t sub 2 of g of t times small f prime of t times dt. And there is a reason why I included both of these integrals, our integral in terms of x and the integral in terms of t, because the way that I recommend that you go about calculating the area under parametric curves is to first represent the area in terms of x and then convert that integral to be in terms of t. All right, so you're going to represent the area that you want to calculate in terms of x, and then you're going to replace y with what it's equal to in terms of t from your set of parametric equations, and then you'll replace dx with the derivative of the parametric equation for x. That will give you small f prime of t times dt, and then you want to change the bounds of integration from being in terms of x to being in terms of t. Okay, so it's not going to be necessary to memorize this integral in terms of t. Instead, just remember your regular form of an integral in terms of x that represents area, and then just work on converting it or rewriting it in terms of t. And so let's take a look at our first example where I'm going to show you this process of finding the area under a parametric curve. All right, so here's our first example. We want to find the area under the curve represented by the parametric equations on the given interval. And our two parametric equations are x equals t plus 2 and y equals 4 minus t squared. And then the interval for which we want to calculate the area between is from values of t from -2 to +2. All right, now the first thing that I always recommend that you do when you want to calculate the area under a curve represented by parametric equations is to draw a sketch of the area that you want to calculate. And so that's going to involve sketching a graph of the curve represented by your parametric equations. And so let's do that first. I'm going to choose a couple values of t to plug into our parametric equations, and then we'll get the corresponding x and y coordinates so that we can plot those points and then connect them to get a sketch of our curve. And I'm just going to choose integers for t between -2 and 2. So we'll have -2, -1, 0, 1, and 2. And so let's plug each of these values of t into the parametric equations to get their corresponding x, y coordinates. When t equals -2, we'll plug -2 into each equation. So we'll have x equals -2 plus 2. That's going to be 0. So x will be 0 when t is -2. And then y will be equal to 4 minus -2 squared. -2 squared is 4, so we have 4 minus 4, so y will be equal to 0. So our first coordinate point is 0, 0. Then let's look at t equals -1. For x, we'll have -1 plus 2. That will be +1. So our x coordinate is 1. And then for y, that will be equal to 4 minus -1 squared. And -1 squared is +1, so we have 4 minus 1, which is 3. So our y coordinate is 3. All right, then when t equals 0, we'll have 0 plus 2 for x, and 0 plus 2 is 2, so our x coordinate is 2. And then for y, we have 4 minus 0 squared, which is just going to be 4. So we have 2 comma 4. Now when t equals 1, we'll have 1 plus 2 for x, so that's going to be 3. So we'll have 3, and then the y coordinate will be 4 minus 1 squared. 1 squared is 1, so 4 minus 1 is 3. So we have 3, 3 for that coordinate point. And then finally, when t equals 2, we'll have 2 plus 2 for x, which is 4. So we'll have 4. And then for y, we'll have 4 minus 2 squared, which is 4 minus 4, which is 0. So our y coordinate is 0. All right, so now we have 5 coordinate points that we can plot to sketch the curve represented by these parametric equations. And so let's draw a coordinate system. I'll draw the y-axis, and then I'll draw the x-axis. And then let's label them. This is the y, and this is the x. All right, and so let's plot each of our points. Our first point is when t equals -2. That's at the point 0, 0. And so that's the origin. So I'll plot that right at the origin here. That is where t equals -2. Then our next point is 1, 3. So I'm going to say that this is x equals 1, and this is y equals 3. And so our next point will be right here. That is when t equals -1. And then our next point is 2, 4. And so this will be x equals 2, and this will be y equals 4. So our next point will be right here, and that is when t equals 0. And then our next point is 3, 3. And so if this is x equals 3, then our point 3, 3 will be right here. And so I'll plot that. That is when t equals 1. And then our next point is when t equals 2, which is 4, 0, which if this is x equals 4 right there, then 4, 0 will be right here. That is when t equals 2. And so now we can connect these points to create our curve. So I'll do that. I'll connect these points to create the curve represented by these parametric equations. And because this curve starts at this point where t equals -2, this would be our initial point for this curve. And it's going to end over here where t equals 2. That's the terminal point. Then we know that the direction of this curve is this direction, from this point to this point. So I'll draw some arrows here to indicate the direction of that curve. Okay, and so now that we have our curve, we can see the area that we want to calculate. We know that we want to find the area underneath this curve between these two values of t, which would be this area right here. And so I'll shade that in. This is the area that we want to calculate using a definite integral, and we're going to start by representing it in terms of x, and then we're going to convert it to be represented in terms of t for our parametric equations. All right, so that's the area that we want to find. And now in terms of x, we know that this area will be equal to some integral from x equals a to x equals b of some function y, that's in terms of x, times dx. All right, and so if we look at our area here, the area that we want to calculate, in terms of x, our bounds of integration will be from 0 to 4, right? Those are the two values of x that our region lies between. So we could rewrite those bounds of integration to be from 0 to 4. All right, and so if we knew the rectangular equation that represents this curve, we could set up this definite integral in terms of x and calculate that area. Now that would involve eliminating the parameter within our parametric equations here and solving for y in terms of x, and we'll do that later to show you that you will get the same answer as you will when you work in terms of t. But before we get there, I want to show you how you take this integral in terms of x and convert it to be in terms of t. And so the first thing that we want to do here is change our bounds of integration. All right, so this area is going to be equal to an integral in terms of t, and so we want to have bounds of integration in terms of t. And so what will those bounds be? Well, they have to be the values of t that correspond to the values of x that we have in our integral in terms of x. And so when x equals 0, that corresponds to this point right here, where t equals -2. And you could also see that from our table here. When x equals 0, t is -2. And so our lower bound will be -2. And then our upper bound is when x equals 4, and x equals 4 when t equals 2. And again, you could see that from this table. When x equals 4, t is 2. So our upper bound will be 2. Okay, and now what we want to do is replace y with what it's equal to in terms of t. And we know from our set of parametric equations that y is equal to 4 minus t squared. So we can write in 4 minus t squared for y. All right, and now all that's left is to rewrite dx in terms of t. We want to have some function times dt. And so we can find that by taking the derivative of our parametric equation that represents x. All right, so in this case, dx dt, the derivative of x with respect to t, will be equal to the derivative of t plus 2. Now the derivative of t, that's just going to be 1, because when you take the derivative of a variable to the first power, it's just going to be equal to its coefficient, which in this case is 1. We have 1t. And so dx dt is just going to be equal to 1, because then the derivative of 2 is just 0, because the derivative of all constants is 0. All right, and so we have dx dt is equal to 1, but we want to know what dx is equal to, so we need to multiply both sides by dt to solve for dx. And that will give us that dx is equal to dt. All right, and so in this case, we have a pretty simple substitution. Dx can just be replaced with dt because dx is equal to dt. So if we do that, we can replace this dx with dt and have 4 minus t squared times dt. And now we have a definite integral in terms of t that represents the area beneath this parametric curve. Okay, and so now all that's left to do is to solve this definite integral for the area. And so if I clean up my work, let's solve this integral by first integrating each of these terms. Remember that the integral of a constant like 4 will just be that constant times the variable that we are integrating with respect to. In this case, we're integrating with respect to t, so the integral of 4 will be 4t. So this will be equal to 4t. And then we're going to be subtracting the integral of t squared. And in order to integrate t squared, we need to use the power rule for integration. And that involves adding 1 to the exponent and then dividing by that new exponent. So 2 plus 1 is 3, so we'll have t cubed, and then we will divide by that new exponent of 3, and so we will divide by 3. All right, and that will be evaluated from negative 2 to 2. And so let's continue our work up here. That will be equal to this expression evaluated at 2, and then we're going to subtract the evaluation at negative 2. So we'll have 4 times 2 minus 2 cubed divided by 3 minus, and remember to put both of these terms in parentheses, 4 times negative 2 minus negative 2 cubed divided by 3. All right, now 4 times 2 is 8, so this will be equal to 8 minus 2 cubed, which is also 8 divided by 3. So we'll have 8 thirds, and then we're subtracting 4 times negative 2, that's negative 8, so we'll have negative 8 minus negative 2 cubed, that will be negative 8, and we're dividing by 3. So we have negative 8 thirds. Okay, now we're subtracting negative 8 thirds, so those two negatives will cancel out. So I can erase this negative and have negative 8 plus 8 thirds. And then if we distribute this negative through this quantity, we'll have that this is equal to 8 minus 8 thirds, and this negative will make this negative 8 positive 8, so we'll have plus 8, and then this negative will make this positive 8 thirds negative, so we'll be subtracting 8 thirds. All right, so we have two 8s that can combine to be 16, so this is equal to 16, and then we have a negative 8 thirds and another negative 8 thirds. Those will combine to be negative 16 thirds, and 16 would be the same as 48 thirds. Right, if we multiply 16 by a form of 1 of 3 divided by 3, that will give us 48 thirds. So this is equal to 48 thirds minus 16 thirds. And 48 minus 16 is 32. And so that will give us our final answer that the area is equal to 32 thirds. That is the area beneath this parametric curve, or this curve represented with these parametric equations. All right, so that's the process. That's how you first set up the area with a definite integral in terms of x, and then rewrite it to be an integral in terms of t so that you can find the area beneath that curve. All right, now there is an alternative method, and I mentioned this earlier. What we could do instead is eliminate the parameter in our parametric equations to get the corresponding rectangular equation and replace y in our definite integral with respect to x with that rectangular equation, and then integrate in terms of x. And so we're going to do that. I want you to see that that will give you the same exact answer. And so there are two different ways to go about these problems, at least when you can solve for y in your rectangular equation. And we'll talk about that more in a moment. What we want to do here is eliminate the parameter in our parametric equations and find that rectangular equation in terms of x and y and solve for y. All right, so let's do that. In order to eliminate the parameter, we need to solve for t in one of these two equations and then substitute what t is equal to into the other equation. And so in this case, I'm going to solve for t in our equation for x. That looks like it's going to be a lot easier. All we have to do is subtract 2 from both sides, right? If we do that, we'll have x minus 2 is equal to t. We just subtract 2 from both sides of the equation. So t is equal to x minus 2. So we can replace t in our equation for y with x minus 2. So we'll have y is equal to 4 minus x minus 2 squared. And we're going to want to expand this. We're going to want to write out all the terms that x minus 2 squared will give us. So let's do that really quick. Let's square this quantity. And I'm going to use the shortcut. We'll start by squaring the first term. So we'll have y is equal to 4 minus x squared. Then our next term will be these two values multiplied together, multiplied by 2. So we'll have x times the negative 2. That's negative 2x times 2 would be negative 4x. So we'll have minus 4x. And then our last term will be negative 2 squared. And negative 2 squared is positive 4, so we'll have plus 4. All right, and then if we distribute this negative through this quantity, we'll find that y is equal to 4 minus x squared plus 4x minus 4. All right, and now we have a positive 4 and a negative 4 that will cancel out, right? 4 plus negative 4 is 0, and so y is equal to negative x squared plus 4x. All right, and so now we have a rectangular equation in terms of x and y that is solved for y that represents this curve. So we can replace y in our definite integral in terms of x with this rectangular equation. So the area will be equal to the integral from 0 to 4 of negative x squared plus 4x times dx. Okay, and so now let's solve this definite integral and let's see if we find that same area that we found when we used an integral in terms of t. All right, so if we integrate each of these terms with respect to x, negative x squared, we need to use the power rule for integration. So we'll add 1 to the exponent and divide by the new exponent. So this will be equal to negative x cubed divided by 3. And then an integral of 4x, we need to add 1 to that exponent and divide by the new exponent. So we'll have 4x squared divided by 2. And then that is evaluated from 0 to 4. All right, now 4 divided by 2 is 2. So we can simplify this. And so I'll write that up here. That is equal to negative x cubed divided by 3 plus 2x squared. And that will be evaluated from 0 to 4. And so now what we want to do is evaluate these terms at 4 and subtract the evaluation at 0. But note that the evaluation at 0 will just be 0 because 0 cubed divided by 3 is 0, plus 2 times 0 squared is also 0. So we have 0 plus 0. So we'd just be subtracting 0. So all we have to do is plug in 4 in this case. So this will be equal to negative 4 cubed divided by 3 plus 2 times 4 squared. All right, just remember that you are subtracting 0 there when you evaluate this expression at 0, but I don't really have the room to write that, so I just wrote out these two terms where we plug in 4. All right, now to simplify, 4 cubed, that's equal to 64. So this is equal to negative 64 divided by 3. And then we have 2 times 4 squared. 4 squared is 16 times 2 is 32. So we have plus 32. And 32 would be the same as 96 thirds if you multiplied it by a form of 1 of 3 divided by 3. And so if I clean up my work, this integral will be equal to negative 64 thirds plus 96 thirds. And negative 64 plus 96 is positive 32. And so this is equal to 32 thirds. The same exact area that we found when we calculated it using the integral in terms of t. And so it doesn't matter which method you use. Sometimes it will be easier to work in terms of x rather in terms of the parameter. But in most cases where you're going to be asked to find the area under a curve represented by parametric equations, the rectangular equation that you get from eliminating the parameter most likely will not be able to be solved for y. What I mean by that is you might end up with some complicated equation where it will be difficult to solve for y, or even when you can solve for y, it may be the case that the resulting rectangular equation is not easily integrated. All right, and so it's in those cases where integrating with respect to t is going to come in handy. And that's particularly going to be the case when you're working with parametric equations that are represented with trig functions. And so before we end this lesson, I want to show you one more example where we calculate the area under a curve, but where it's going to be necessary for us to work in terms of t, because finding the rectangular equation and then solving for y isn't really going to be an option. And so let's take a look at that next. All right, so here's our last example. We want to find the area under the curve represented by the parametric equations. In this case, we have x equals 2 times cosine t and y equals 3 times sine t. All right, now you'll notice in this case that the directions don't tell us to find the area for a particular interval of t. And when that happens, it's most likely the case that the area you're looking at is an area within a closed loop. In other words, the curve represented by our parametric equations are some form of a circle or an ellipse or some curve that encloses a region. All right, now if you're familiar with your parametric equations by this point, you probably know that when you have a set of equations where x equals some constant times cosine and y equals some constant times sine, that you're either working with a circle or an ellipse. In this case, we're working with an ellipse because that constant out front isn't the same, but I'll show you why that's the case. Let's start by eliminating the parameter and finding our equation in terms of x and y that will help us sketch the graph of the curve, as well as really nail down why we need to work in terms of t in order to calculate this area. All right, so remember, when you eliminate the parameter for a set of parametric equations where you have trig functions, you want to solve for those trig functions and then use a trig identity to rewrite it in terms of x and y. And so in this case, if we solve for cosine and sine, we just have to divide both sides of these equations by their respective coefficient. So for x, we're going to divide both sides by 2, and that will give us that x divided by 2 is equal to cosine t. And then for the equation with y, we want to divide both sides by 3. So we're going to have y divided by 3 is equal to sine t. All right, now to write these parametric equations into a rectangular equation, we need to use the trig identity that sine squared t plus cosine squared t is equal to 1. All right, so if we square both sides of these equations, you can see how we can rewrite the parametric equations into a rectangular equation by making some substitutions into this identity. All right, because sine squared t is sine t squared and cosine squared t is cosine t squared. And so we can replace sine squared t with y divided by 3 squared and cosine squared t with x divided by 2 squared. So what we'll have is that y divided by 3 squared plus x divided by 2 squared is equal to 1. Now if we square the numerator and denominator for both of these fractions, we'll have y squared divided by 3 squared plus x squared divided by 2 squared, and that is equal to 1. And this right here is the equation of an ellipse, right? When you have y squared divided by some value squared, and then you're adding it to x squared divided by some other value squared, and that's equal to 1, that is the equation of an ellipse. If y squared and x squared were both being divided by the same value squared, right? If both of them were 3 squared or if both of them were 2 squared, then we would have a circle, but in this case we have an ellipse. And so you can see in this case that solving for y would be fairly difficult. We could do it, but it would give us a radical function because we would have to take the square root of both sides in order to get rid of this y squared to solve for y. And radical expressions, or expressions involving square roots, can be pretty tricky to integrate, and so it's going to be better for us to work in terms of t. All right, it's going to be a whole lot simpler than solving for y in this rectangular equation and then integrating that with respect to x. Okay, and so if I clean up my work here, let's sketch a graph of the area that we want to calculate. So we need to draw a sketch of the curve represented by these parametric equations, which finding the rectangular equation will actually be helpful in doing. We now know that we're working with an ellipse, and the value squared underneath x and y tells us how far from the center the ellipse stretches in the x and y direction. And so let's graph the ellipse. I'll draw the y-axis here and the x-axis, and let's label them. So this is the y, and this is the x. Now to graph the ellipse, note that y squared is above 3 squared, so we know that the ellipse will stretch 3 units in each y direction. So if this is y equals 3, and this is y equals -3, our ellipse is going to cross through those two values on that y-axis. And then underneath x squared, we have 2 squared, so the ellipse is going to stretch 2 units in each x direction. So if this is x equals 2, and this is x equals -2, then our ellipse will look something like this. All right, now that's not perfect, but it's good enough. And so now you can see that the area we want to calculate is the area within this curve, right? The area beneath this curve will be the area inside that ellipse. And so I'll shade that in. This is the area that we want to calculate. And once again, we're going to use the same process that we used in the previous example. We're going to start by representing this area with a definite integral in terms of x, and then we're going to convert it to be an integral in terms of t. And you're going to see why that is an important strategy with this example. All right, and so we can calculate this area using the following definite integral. The area will be equal to the integral from x equals a to x equals b of y times dx. All right, now in this case, our two values of x that we would want to calculate the area between would be x equals -2 and x equals 2. right? So I'll rewrite those two bounds of integration. We'll go from -2 to 2, but note that if we were actually going to try to calculate this area in terms of x, that our equation for y would involve a square root, right? I explained this earlier. If we were to solve for y, at some point we would need to take the square root of both sides of the equation to eliminate this square for y. And so our equation in terms of x would involve a square root, which would not account for this entire ellipse. It would only account for half of it, for the positive portion. And so this definite integral as it stands would only be calculating the area from -2 to 2 above the x-axis. And so you've probably done this in the past, earlier in calculus. The way that we can fix that problem is to take advantage of the symmetry of our ellipse and multiply the integral by 2. Right, we can multiply it by 2, and that will double the area that we find in the top half, and that will represent the whole area of the ellipse, because an ellipse is symmetrical, right? The area below the x-axis is the same as the area above the x-axis, because this ellipse is symmetrical about the x-axis, and that's only the case because the ellipse is centered at the origin. I forgot to mention that earlier, that this rectangular equation is the equation of an ellipse, but specifically an ellipse centered at the origin, because we just have y squared and x squared. We don't have y minus some value or y plus some value squared, and we don't have x plus some value squared or x minus some value squared. We just have y squared and x squared, so the ellipse is centered at the origin. And so because of that, we have symmetry along both axes. All right. So multiplying the definite integral by 2 will ensure that we are calculating the area that is enclosed by the entire ellipse, not just half of it. And so this definite integral right here in terms of x would calculate the area inside this ellipse. But we don't want to work in terms of x, we want to work in terms of t. So now what we have to do is convert this integral to be in terms of t. And so typically I like to start with the bounds of integration. And so we have to ask ourselves what values of t correspond to 2 and -2. Now we didn't draw out a table with values of t and the x and y coordinates this time. We just used our rectangular equation to aid in graphing our curve. But we are going to have to determine what values of t correspond to x equals 2 and x equals -2. And so in this case, it might be helpful to plug in a couple values of t into our parametric equations to find their corresponding x and y values. And so let's draw out a small table here. I'll have the t values on one side, and then we'll have our x and y coordinates. All right, and when you're working with a full ellipse or a full circle, it's most likely the case that you're working with values of t from 0 to 2 pi. In fact, if you are familiar with graphing parametric equations by this point, you probably already have an idea of what the values of t will be that correspond to these values of x. But let's just check anyway. Let's see what values of x and y we get for some values of t between 0 and 2 pi. Let's start with t equals 0. When t equals 0, we'll plug 0 into each of these parametric equations. X will be equal to 2 times cosine of 0. Cosine of 0 is 1, so we have 1 times 2. So x will be equal to 2. And then for y, we'll have y is equal to 3 times sine of 0, but sine of 0 is 0, so 0 times 3 is 0, so y is equal to 0. So when t equals 0, our coordinate point is 2, 0, and that is going to be this point right here, right? That will be the point 2, 0. So I'll plot that point. That is when t equals 0. So you can already see that that corresponds to our x value of 2, right? So t equals 0 will be our upper bound. And so if we're going to rewrite this integral in terms of t, let's start by rewriting that bound. This will be equal to 2 times the integral of some lower bound to our upper bound of 0. And then let's do another value of t. Let's look at t equals pi divided by 2. When t equals pi divided by 2, we'll have 2 times cosine of pi divided by 2. And cosine of pi divided by 2 is 0. So we have 0 times 2, which is 0. So our x-coordinate will be 0. And then our y-coordinate will have 3 times sine of pi divided by 2. And sine of pi divided by 2 is 1. So I have 1 times 3, which is 3. So our y-coordinate will be 3. All right, so when t equals pi divided by 2, we'll be at the point 0, 3. And so I'll plot that point. That is when t equals pi divided by 2. But that's not quite what we're looking for, right? We're looking for the value of t that corresponds to this point right here, where x equals -2. So let's plug in another value of t. This time let's work with pi. Let's see what pi corresponds to. If we plug pi into our parametric equations, we'll have 2 times cosine of pi, and cosine of pi is -1. So we'll have -1 times 2. which is negative 2, and so x equals negative 2. Now I'm going to plug in our y-coordinate just to make sure that that will give us this point, but remember that we are looking for the value of t that corresponds to x being negative 2 because that's our lower bound. All right, but when t equals pi, y will be equal to 3 times sine of pi. Sine of pi is 0, so we have 0 times 3, which is 0, so we have negative 2, 0. And so negative 2, 0 is this point right here. We can plot negative 2, 0, and that is when t equals pi. All right, and so we can see the direction of this plane curve now. We now know that we're starting at this point and we're heading in this direction, and we're probably going to come back to this point right here when t equals 2 pi. And so I'm just going to draw the direction here for our plane curve. You can now see the direction that it's heading in, but we don't really need to know that in order to calculate the area. What's important here is now we know the value of t that corresponds to our x value of negative 2. When t equals pi, x equals negative 2, and so our lower bound for our integral when we're working in terms of t will be pi. All right, so we have 2 times the integral from pi to 0 of y times dx. We need to rewrite both of those in terms of t. We know that y is equal to 3 times sine t from our parametric equations, and so we can rewrite y with 3 times sine t. So we'll have 3 times sine t, and then we can find dx by taking the derivative of our parametric equation for x. So let's take the derivative of x with respect to t. If we do that, we'll have dx dt is equal to the derivative of 2 times cosine t, and the derivative of cosine is negative sine. So dx dt will be equal to negative 2 times sine t. All right, so dx dt is equal to negative 2 sine t, but we want to know what dx is equal to, so we want to multiply both sides by dt to solve for dx. And if we do that, dx is equal to negative 2 times sine t times dt. All right, so if we replace dx with what it's equal to, we'll have 3 times sine t times negative 2 times sine t dt. All right, and so now we have our integral that represents the area inside this ellipse in terms of t. Now what we have to do is simplify it and solve it. And so first of all, let's simplify our integrand here, the contents within our integral. We can pull 3 and negative 2 out to the front. So out front of the integral, we'll have 2 times 3 times negative 2. 2 times 3 is 6, times negative 2 is negative 12. So what we'll have is that the area will be equal to negative 12 times the integral from pi to 0 of sine t times sine t dt. Now sine t times itself will be sine squared t, and so I'll just rewrite this, and we will have sine squared t dt. Okay, now one more thing that we can do before we integrate. This isn't a necessary step, but I think it's going to make it look a lot nicer. Notice that we are integrating from pi to 0. Pi is a bigger value than 0, right? Pi is 3.14 and so on. And so usually our upper bound is bigger than our lower bound. And so what we can do here is actually flip those bounds of integration using one of our properties of definite integrals, which is that you can flip the bounds or flip the limits and then multiply your integral by negative 1. All right, so we can flip the bounds and then negate our integral, which in this case will be pretty nice because we have negative 12 times our integral, and so this negative 12 will just become positive 12 when we flip those bounds of integration. All right, so if I clean up my work, we can rewrite this integral to be equal to positive 12 times the integral from 0 to pi of sine squared t dt. Okay, and so now we have a more standard looking integral. We have a lower bound that is smaller than the upper bound, and it's a positive integral, which is nice. And so now all that's left to do is solve this integral. And we can find the area under the curve represented by these parametric equations, or in other words, the area inside this ellipse. All right, now in this case, we have a trigonometric integral. This is a type of integral that we learned how to solve earlier in Calc 2. And so if you're not familiar with solving trigonometric integrals, I would recommend that you go back and review that a little bit, because a lot of these problems with calculating the area under parametric curves are going to involve solving trigonometric integrals. All right, now in this case, the method that we would use to solve this integral, since we have just sine squared t, would be to use a half angle identity. And that half angle identity looks like this. We know that sine squared t will be equal to 1/2 times 1 minus cosine of 2t. All right, and so what we're going to do is replace sine squared t with 1/2 times 1 minus cosine 2t, and that will help us solve this integral. So this will be equal to 12 times the integral from 0 to pi of 1/2 times 1 minus cosine 2t times dt. All right, now this 1/2, we can bring that out to the front. 1/2 times 12 will be 6, and so we can rewrite this integral to be equal to 6 times the integral from 0 to pi of 1 minus cosine of 2t dt. All right, and now the next step we want to take is to split this up into two integrals, right? Because we can integrate one separately from cosine of 2t. Integrating cosine of 2t is going to involve using u substitution. It's a very simple u substitution, but we do need to use it. And so let's split up this integral into two integrals. This will be equal to 6 times the integral from 0 to pi of 1 dt minus 6 times the integral from 0 to pi of cosine 2t dt. All right, now I had to write that pretty small, so if I clean up my work a little bit, this will be equal to 6 times the integral from 0 to pi of 1 times dt, which is just dt, minus 6 times the integral from 0 to pi of cosine 2t dt. All right, that's the same thing we have right here, just written a little bit more nicely. Okay, and so now we can begin to solve further. We know that the integral of 1 dt is just going to be t, right? The integral of 1, a constant, will just be equal to that constant times the variable of integration, which is t. And so this will be equal to 6 times t evaluated from 0 to pi. And then we'll subtract this integral. And we want to use u substitution here because we have a composite function of cosine 2t. Right? If we had cosine of just t, then we could just integrate it into the sine function. But in this case, we have cosine of 2t, so we need to use u substitution. We need to set u equal to that inside function of 2t. So if we do that, u will be equal to 2t. And then if we take the derivative of that, du dt will be equal to 2. The derivative of t to the first power will just be equal to the coefficient, which is 2. And then if we solve for du, that will give us that du is equal to 2 dt. And so we want to substitute du into our integral. So we have to find 2 times dt, but I only see a dt. So let's divide both sides by 2, and we'll have that du divided by 2 is equal to dt. And now we can see that we can replace dt with du divided by 2. All right, so our integral will be 6 times the integral from t equals 0 to t equals pi of cosine of u times du divided by 2. All right, now I wrote our bounds as t equals pi and t equals 0 because the rest of our integral is in terms of u, and I don't want us to forget that those bounds are still values of t. But we can change them to be values of u. All we have to do is plug those values of t into the equation for what we set u equal to. So let's do that. When t equals pi, we'll have 2 times pi is u, so u will be equal to 2 pi. So I'll erase this, and our new bound will be u equals 2 pi. And then for the lower bound, when t equals 0, we'll have 2 times 0, and so u will be equal to 0. And so that bound won't change, but I'll erase it and write u equals 0 anyway. So we'll have u equals 0. And so now there's no need for us to rewrite our integral back in terms of t. We can just integrate with respect to u, and then evaluate at our bounds of integration. Okay, so if I clean up my work, if we evaluate t at pi and subtract the evaluation at 0, that's just going to be pi, right? We're going to have pi minus 0. We're just replacing t with each of those bounds. And so this will be equal to 6 times pi because pi minus 0 is pi. So we have 6 pi minus this integral, but let's bring this 1/2 out to the front. 6 times 1/2 is 3. So we'll have 3 times the integral from 0 to 2 pi of cosine u du. Now the integral of cosine is sine, so this will be equal to 6 pi minus 3 times sine u evaluated from 0 to 2 pi. All right, and so now to solve this integral, we need to evaluate sine at 2 pi and subtract the evaluation of sine at 0. But note that sine of 2 pi is 0 and sine of 0 is also 0. And so this whole part of our calculation is just 0. This will be 0 times negative 3, which is 0. And so we just have 6 pi minus 0. All right, so I'll write that up here. Our final answer is that the area is equal to 6 pi. This whole term becomes 0. All right, and you could plug in 2 pi and 0 into the sine function if you wanted to check that for yourself, but I'm telling you that you will get 0 for that, and so our final answer is just 6 pi. The area under the curve represented by these parametric equations, or inside this ellipse, is 6 pi. All right, and so with that, this was the last example for this lesson, but if you want to see more examples of finding area under parametric curves, feel free to watch my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.